In this lecture, I will solve some selected numerical problems from the exercise of chapter 11 on the topic of energy methods from the book of Mechanics of Materials by Beer and Johnston, 7th edition. The first problem, the simplest one which I have chosen to solve in this lecture, is problem number 11.2. This is the simplest type of problem which I have chosen because in the beginning the basic concepts or some formulas need to be understood by the students. One of the very simple formula for strain energy density is U is equal to sigma x square, which is normal stress in x direction or any other direction you can use, divided by 2E. E is modulus of elasticity. This expression is for elastic strain energy density, because we are using E, so it is for elastic range. The problem states as determine the modulus of resilience for which the following aluminum alloys part A, part B and part C. In three parts, three different alloys have been given. Part A is aluminum alloy 1100H14, for which E is 70 gigapascal and yield stress is 55 megapascal. Since they have asked modulus of resilience, what is modulus of resilience? I will recall it a little bit. Modulus of resilience is area under the stress strain curve until yield stress only. This is modulus of resilience. So we can use this above expression with a slight modification. Modulus of resilience is Uy, which is equal to sigma yield square divided by 2E. Do not get confused with this x and y. This x is direction, x direction. If the stress is in y direction, it can be y, it can be z. It is a unidirectional stress. This y, capital Y, is yield stress. For a unidirectional tensile load test, we can draw stress strain diagram where sigma y is yield stress, the point where the material will start deforming permanently. So we will use this expression for these three parts. I will solve the first part, you can do the rest of the two parts, they are similar. So let us move towards the solution. Uy, it is problem number 11.2. Uy is equal to sigma y. This capital Y is for yield strength. Small y is used for y direction. So don't be confused with it. Sigma y square. Okay, sigma y square divided by 2E. Okay, sigma y is given in the first part. It was 55 megapascals, 55 into 10 power 6 pascals square divided by 2 into E. E is given. E was 70 gigapascal. 70 into 10 power 9. So it is a simple calculation. Uy will become 21.6 into 10 power 3 joule per meter cube, or you can write it as joule is actually Newton meter. So this formula in some books it is written as meter Newton per meter cube. So don't be confused. Don't get confused with it. Joule per meter cube or Newton meter per meter cube is same. Okay. This was the simplest problem. You can solve rest of the two parts by yourself with the same formula. I will move further to a different problem in a different difficulty level. The next problem which I have chosen for this lecture is problem number 11.9. It is a uniform, it is a bar ABC. AB has a different diameter and BC has a different diameter. They are under axial load P. Length of both the bars is given. Using E equal to 29 into 10 power 6 psi, determine the strain energy of steel rod ABC when P is equal to 8 kilopounds. Load is given 8 kilopounds. Strain energy of rod ABC. So we have to find strain energy means capital U for the whole rod ABC. Strain energy will be different for rod AB, and then again it will be different for rod BC, and then we can add them up. Expression for strain energy under normal load is, we have studied this topic in our theory lecture, it is equal to P square L divided by 2AE. So for section AB and for section BC we will calculate it separately and then we will add it up. It can be added, it is a scalar quantity, so it can be added directly. Okay, and part B, P is same for both of them. P is same, it is applied at the end, so it is same for both AB and BC. Length for AB is 2 feet, for BC it is 3 feet. Area as the diameter of both of them is given, so area can be found. E is same for both of them, which is 29 into 10 power 6 psi. Okay. Part B is determine the corresponding strain energy density in portion AB and BC. In part A, total U was required, sum of AB and BC. In part B, strain energy density, small u, it is required small u is equal to capital U divided by V, volume, R. We can write it as sigma x square, x is direction. For example, if we consider it x direction, if it is y, we can write it here y. If it is z, we can write it to z divided by 2e. We can use either this expression or this one to calculate small u. But we are required to find small u for section AB separately and for section BC separately. So let us move towards our solution. Problem 11.9. Okay, first we need to find area for rod AB. It is pi by 4 to diameter of AB. Diameter of AB is 5 by 8 inch. So pi by 4, 5 by 8 power 2, it becomes 0.307 square inch. Similarly, area of rod BC is pi by 4 diameter of rod BC square. Rod BC has a diameter of 3 by 4 inches. So square of 3 by 4 into pi by 4, it becomes 0.442 square inch. Okay, capital U in part A, it was asked to find, okay, let me just mention it here. I have solved the problem 11.2 for part A only. Okay, In part A of problem 11.9, it was asked to find total U for ABC. So it is UAB plus UBC. ABC has two parts, AB and BC. So it will be P square, PAB square LAB divided by 2E 2A AB into E AB plus PBC LBC divided by 2ABC EBC. P for AB and BC are same in this problem. In some other problem, it can be different. For example, if you are given a different load here, P1 some other value, then you have to section it here, and you have to find P for AB different and BC different. We have done such kind of problems in our chapter number 2, which is regarding axial loads, and you can be asked for such problems in your exams. So please be prepared for such kind of problems. Okay, let us move. P is same for both AB and BC, so we will use P equal to 8 kilopounds. Length AB is 2 feet, length BC is 3 feet. Area has been found already. E is same for both of them, 29 into 10 power 6 psi. Okay, so let us put the values. PAB and PBC both are given 8 kilopounds, 8 into 10 power 3 square. Length of AB is given as 2 feet, so 2 into 12 inches divided by 2. Area of AB has been calculated. E is given 29 into 10 power 6 psi. Okay, plus similarly PBC is same, 8 into 10 power 3 pounds. LBC is 3 feet, so 3 into 12 inches divided by 2 into area of BC is given 0.442 into E is given 29 into 10 power 6. So by simplifying the above terms, U can be calculated as 176.13, and the unit is inch pound. Okay, so total U for section for rod ABC has been calculated. In part B, we were asked to find small u, strain energy density. Remember, capital U is strain energy, small u is strain energy density, which is strain energy per unit volume. Okay, UAB will be equal to sigma AB square divided by 2E. E is given, sigma AB can be calculated. Sigma AB is equal to PAB divided by area of AB. PAB is given in the problem, 8 into 10 power 3. Area of AB has been calculated already. Above it is 0.307. So it becomes almost 26.05. 86 into 10 power 3 psi. So UAB small u, it is 26.0586 into 10 power 3 square divided by 2 into 29 into 10 power 6, and after calculation it can be calculated as 5.654, and the unit of strain energy density is inch pound per cubic inch. Okay. For BC, rod BC, strain energy density will be sigma BC square divided by 2E. E is same for both AB and BC, that is why I am using the same E. Sigma BC is equal to PBC divided by area of BC. P is 8 into 10 power 3. Area of BC is 0.442. Okay, 8 divided by 0.442, 18.099. Into 10 power 3 psi. Putting the values here, sigma BC, UBC will be 18.09 to 10 power 3 whole square divided by 2 into 29 to 10 power 6. So UBC becomes 5.653 inch pound per cubic inch. And there's one mistake, this first one, this one, UAB, and there's a mistake in calculations. This is not 5.654. UAB was, if you do the calculations by yourself, it was 11.723 unit is same. So UAB and UBC have been calculated, which were required in part B of the problem. So what we have done in part A, strain energy was required for whole rod ABC, which is capital U. Expression is P square L by 2AE. So there are two parts, UAB and UBC. We have added them. In part B, small u, strain energy density, was required separately for both AB and BC rods. So the expression is sigma square divided by 2AE. We have found sigma AB and divided by 2E. Similarly, sigma BC divided by 2E, and we have calculated both UAB and UBC. Okay, let us move towards our next problem. Problem number 11.11. 11. This is a bit advanced problem as compared to the previous two problems. Here is an assembly of two pipes The statement is a 30-inch length of aluminum pipe of cross-section area 1.8 square inch is welded to a fixed support A. Okay, this pipe CD, this pipe is welded at point A and point C as well, but here they have mentioned at point A, and to a rigid cap to a rigid cap B. Here this is a rigid cap. So the pipe, this pipe is attached to the rigid pipe at E and D and welded at point A and C. So this pipe is between point CD and point AE. Okay. The steel rod EF, here is the steel rod EF of 0.75 inch diameter of this pipe. This rod is given. For the previous pipe, area was given, now diameter is given. It is welded to cap B. Here it is welded to cap B. Knowing that the modulus of elasticity is 29 into 10 power 6 psi for steel, this rod is steel, so its E is given 29 into 10 power 6 psi, and 10.6 into 10 power 6 psi for aluminum. This pipe is aluminum, its E is given as well. In part A, we are asked to determine the total strain energy of the system when P is equal to 8 kilopounds. Total strain energy. U is required, capital U, strain energy. So, total strain energy will be sum of the strain energy of this rod EF plus this pipe CD or AE. You can call it CD or AE. This is part 1, part A. In part B, okay, P is given here, 8 kilopounds. In part B, the corresponding strain energy density of pipe CD and rod EF. Strain energy density, small u, for this pipe CD is required and rod EF is required separately. It is similar to the previous problem. The statement is similar. Difficulty level is a little different. Okay. Here I want to discuss a few things before going towards solution. When we apply force of 8 kilopounds here at point F, this rod EF of length 48 inch is under a tensile load of 8 kilopounds. This load, this rod is pushing the pipe CD inside or towards right side, and this weld is pushing it towards the left. So the pipe CD or pipe AE, both are same actually. This is whole pipe cross section is shown. This pipe CD is under compression and rod EF is under tension. The value of the force is same for both of them. P is 8 kilopounds for EF tensile. P is compressive 8 kilopounds for pipe CD. So we will use P equal to 8 kilopounds, positive for EF and negative for CD. Let us move towards our solution. First we have to find U. Problem number 11. U CD, for pipe CD, it is minus P because it is compressive, LCD divided by 2AE. So it is minus 8 into 10 power 3 square. Length of the CD is given 30 inches. 30 divided by 2 into area and E are given. Area of CD aluminum pipe is given as 1.8 square inch, 1.85 square inch, and E is given 10.6 into 10 power 6. 1.85 and 10.6 into 10 power 6. So UCD becomes 48.95 inch pound. EF, for rod EF, it is under tensile load P square LEF divided by 2 area of EF into E. E is same for both of them, so I am writing E it simply. P is 8 into 10 power 3. Length of EF is 48 inches. Area of EF can be found from this diameter 0.75. E is 29 into 10 power 6. To pi by 4. It becomes 119.89 inch pounds. Okay, we have calculated capital U for CD and EF separately. So total U will be sum of UCD plus UEF. You can add these two numbers. So total U will be 168.8 inch pound. This was required in part A, total strain energy. In part B, we were asked to calculate separate strain energy densities for pipe CD and pipe EF, rod EF. Okay, for that strain energy density is actually equal to sigma square divided by 2E. E is different for both of them, sigma is different for both of them. Sigma CD is equal to force divided by minus P is there, minus P divided by area of CD. So is 8 into 10 power 3 divided by 1.85, which becomes minus 4.324 psi. UCD, small u, will be equal to sigma CD square divided by 2 ECD. ECD is E of aluminum, 10.6 into 10 power 6. By putting the values, you can find sigma CD equal to, first let us put values here, minus 4.324 square divided by 2 into 10.6 into 10 power 6. So UCD, small u, is 168.8 inch pound per cubic inch. Similarly, sigma EF is equal to P over AEF. So it is 8 into 10 power 3 divided by pi by 4, 0.75 square. It becomes 181 0.08 psi, and if we put the values in the expression of UEF, it is sigma EF square divided by 2 EEF. So 18108 divided by 2 into EEF is 29 into 10 power 6. So UEF becomes 5.65 inch pound per cubic inch. Sorry, here's a mistake in this calculation of UCD. This value is wrong. Let me correct it. Steps are fine, just the calculations have some mistake. This 168.8 is wrong. It is 0.882. 168.8 was the answer for the first step. That is 0.882. Please make the correction. What we have done is, in the first part we were asked to find total strain energy. So total strain energy is sum of the strain energies for all of the individual parts. So individual parts were pipe CD and rod EF. So we have found capital U CD and capital U EF. Formula is given, P square L divided by 2AE. E is different for both of them. For EF it is different, and for CD it is different. Okay, similarly we have added both of them to find total U. In part B we were asked to find strain energy density, which is small u. Small u is equal to sigma square divided by 2E. So sigma for part CD, for pipe CD and rod EF are different. P divided by ACD and P divided by AEF. For CD it is under compression, so it is negative. But in the next step it is sigma square, so the negative will become positive again. UCD is sigma CD square divided by 2ECD, and UEF is sigma EF square divided by 2EF. Putting all the values, we have calculated numerical values of UCD and UEF, strain energy densities for part CD, for pipe CD and rod EF. Okay, let us move towards our next problem, which is a little more complicated. What is it? There are 3 plates. This plate, you can see it. It is plate AE, or steel plate. And let me first read the statement, you will understand it. A single 6 mm diameter steel pin B is used to connect the steel strip DE. This is steel strip DE, shown in the blue color, to 2 aluminum strips, each of 20 mm wide and 5 mm thick. Here are 2 aluminum strips, this one a grey color one, and here at the bottom. They are connected to the steel strip using a pin at point B. This pin is made with steel and the diameter of the pin is 6 mm. Okay, these plates are given as 20 mm wide and 5 mm thick. 20 mm is its width, and thickness in third dimension it is 5 mm. Okay, and length is also given 0.5 meter. The modulus of elasticity is 200 gigapascal for steel. For this plate it is 200 gigapascal, and 70 gigapascal for aluminum. For these 2 plates it is 70 gigapascal. knowing that the pin at B, the allowable shearing stress is 85 megapascal. T allowable for this pin, it is 85 megapascal. Determine for the loading shown the maximum strain energy that can be acquired by the assembled strips. Maximum strain energy means the total strain energy of this assembly if we do not exceed tau allowable. So we have to find U total. U total will be sum of U dE plus 2 times some D is the steel plate and there are 2 plates AC of aluminum. So sum of the plate DE plus 2 times sum of the energy of plates AC. There are 2 plates like AC aluminum plates. So we will find their strain energy and then add up. What we can do in this problem, there is some complication which I want to explain here. What is the complication? This force P is pulling the plate DE towards the right side. Here, these 2 plates, aluminum plates, will pull back towards the left side. This pin is under shear. Pin B is under shear. If I draw pin B here, it is under double shear actually. First we have to find this load P because P is not given. So we can find P from this tau allowable. Tau allowable is given. So tau allowable can be used to find load P because it is under double shear. Okay. Now area of the pin can be calculated from diameter of the pin, which is given as 6 mm. So we can find P here. Now we will need the areas of the plate. What is U actually? P square L divided by 2 AE. So we will need length. P can be found from this expression. We will need length of each plate, area of each plate, and E of each plate. E is given for both steel and aluminum. Length of each plate can be found from this figure. This plate AC has a length of 0.5 meter. Similarly, this bottom plate is also of same length. Plate DE, the total length is given as 1.25, but whole of the length is not under force or under tension. This plate is under tension between point B and point E only. This part of the plate is free. There is no force on this plate DE beyond point B. This plate is under tension between this point E and point B only. So we will consider this length only, which is 1.25 minus 0.5, which is almost 0.75 meter. So we will take the length of plate B as 0.75 meter. Why? I will explain it again here. Let us see it again. Plate DE, which is blue color plate, which is made of steel, it is under force P, tensile force. When we apply this force P here at point E, this force travels is transferred from E until B. At point B, the pin resists this tension, this force at this point. Then rest of the part of this plate is free. There is no force in this part, the 0.5 length of part. So only this part of the plate is under tension, and we will use this length 1.25 minus 0.5, which is equal to 0.75. Areas of each plate, since thickness and width of each plate is given, width of this plate is 20 mm and thickness is 5 mm. Similarly, width is 20 mm and thickness is 5 mm. So we will use 20 into 5 as area of the plates. Okay. Here 20 into 5. Okay, let us move towards the solution. Problem 11, 12. Area of the pin is pi by 4 diameter of the pin square. Diameter of the pin is given, which is 6 mm, so 0.006 meters. It becomes 28.274 millimeter square. Okay, P is equal to, or tau allowable equal to P divided by 2 times area, because there is double shear. I have explained it already. So P will be, this is area of pin, P will be 2 times tau allowable into area of the pin by putting all the values. Tau allowable is given here, it is 85 megapascal. We can use millimeters with megapascals. 2 into 85 into 28.274. So P becomes 4806.58 newtons. This P, here we can see it is applied at point E. So P for this plate DE is 4806.58, but for this plate AB and DB, it is different. Here this P is between BE only, between this portion only. For AC, I will make it clear here. This direction, it is PBE. Here the pin is resisted by PAB and PDB. This is PDB, this is AB, and PDB, and this is PBE. So PB is same, PAB and PDB are half of the P. So I will write here PBE is 4806.58. Rest of the loads are half. PAB and PDB are half of the P, is equal to 2403.29 newtons. Okay. Length of BE, as I have discussed earlier, it is 1.25 minus 0.5, so it is 0.75 meters. length of AB and DB both are given here, which is 0.5 meter. Length of AB and length of DB both are same, 0.5 meter. Okay. Areas are 20 into 5 mm. 20 is width and 5 is thickness. So let us put all the values in the expression. Total U is equal to UBE plus UAB plus UDB. So UBE will be PBE square into length of BE divided by 2 area of PE to E for BE plus force on AB square length of AB divided by 2 into area of AB E of AB plus PDB square length of DB divided by 2 times area of DB E of DB. All of these values are known. Okay, PBE, PAB and PDB all are calculated here. Length of BE, length of AB and length of DB are known. Area of PE, area of AB and area of DB all are same. I will write it here. Area AB, area, this is area can be calculated from thickness and width of the plate, which is same for all of the plates given. into 5 mm, so it becomes 100 millimeter square. Okay, EBE, EAB and EDB. E is given in the expression. E for the modulus of elasticity is 200 gigapascal for steel. This strip BE is steel, so we will use EBE as 200 gigapascal and 70 gigapascal for aluminum. So AB and DB are 70 gigapascal. E of AB and DB. By putting all the values, you can do the calculations by yourself. I will write the numerical value directly. It is 0.8458 into 10 power minus 3 Newton millimeter. Or you can write it U equal to 0.8458 Newton meter. Okay. What we have done, we have calculated separate strain energies for part B, for plate BE, plate AB and plate TB. You just need to calculate correct lengths, because you have to calculate length from the pin to the load application point. In this diagram we can see here is pin. From pin to the load application point we have calculated length for plate BE. Actually it is plate DE, but part DB is actually under no load. Okay. Similarly for the aluminum plates, part AB is under load between fixed point and between pin. Similarly this plate is under load between point D and point B. So by calculating the correct lengths, area is given, actually thickness and width is given. Load, since it is under double shear, so load will be can be calculated from double shear formula. Total U can be calculated from this expression, P square L divided by 2AE. Okay. we will move further towards our next problem, which is problem 1133. It is from shear force or torque under torque loading. The statement is in the assembly shown, torques TA and TB are exerted on discs disc A and disc B. So here TA is 300 Newton meter and TB is 400 Newton meter respectively. Knowing that both shafts are solid and made of aluminum, this shaft BC and shaft AB are made of aluminum. They are solid, they are not hollow. G is given as 73 gigapascal. Determine the total strain energy acquired by the assembly. Total strain energy is required. Total strain energy will be strain energy by shaft AB plus strain energy of shaft BC. Okay, under torsion, under shear load, we have discussed in our theory, U is equal to T square L over 2GJ. So we have to find torque for part AB, length of AB, J of AB and G of AB plus torque for BC, length of BC, 2 into G of BC divided by length of J of BC. Okay. Length for both the sections are given 0.75, 0.9. J can be calculated from diameters. Diameters are given 30 mm and 46 mm. G is given, it is same for both, 73. Only torque is left. We have to section the this assembly between BC and between AB to calculate torques separately. We have already done this in chapter number 3 to calculate torques in different shafts. Okay, first we will section this between AB, and we can see here is torque 300 Newton meter. This is point A. So here will be TAB, which will be equal to the first torque 300 Newton meter. Again, sectioning between B and C. Here is torque 300 Newton meter. Here is torque 400 Newton meter. Here will be reaction TBC. So it will be sum of the above two torques, 300 plus 400, it is equal to 700 Newton meter. So this has been done in chapter 3 already. I hope you understand it. TAB and TBC are calculated. We will use these two torques in our solution. Let us move towards solution. Problem number 1133. Torque AB is 300 Newton meter. Torque BC is 700 Newton meter. I have done it earlier. Total U is equal to UAB plus UBC, which is equal to TAB square, length of AB divided by 2 G of AB, J of AB, plus TBC square, length of BC, 2 into G of BC, J of BC. Okay, T has been calculated, lengths are given, G is given. You can calculate J, we have already done it. So by putting all the values, you can put all the values by yourself. I will do it here directly. It is 6.977 plus 5.726 separately for the two terms. So total U becomes 12.7 Joule or Newton meter. Just I have left J. You can find J by yourself. J is equal to pi by 2 radius power 4. So you can do it by yourself. Radius of both the shafts are given, radii for both the shafts. It is 46 for shaft BC and 30 for shaft AB. So what we have done, we have calculated torques in both the sections, section AB and section BC, by sectioning the shaft between AB and BC. We have applied summation of torques expression using statics. We have found torque AB and torque BC, and then simply putting all the values in this expression, we have calculated total U. Okay, one more problem I want to solve. Problem number 1136. The state of stress shown occurs in a machine component made of a brass for which sigma y is 160 megapascal. Yield strength is given. This sigma y, remember it, it is capital Y, so it is yield strength. Here a y is written small y, it is y direction. So this sigma y is small y, 20 megapascal. This sigma capital Y is stress, yield stress. Using the maximum distortion energy criteria, von Mises criteria, which we have studied in chapter number 7 as well, and I discussed it with you in our theory, von Mises criteria, or maximum distortion energy criteria. Determine the range of values of sigma z for which yield does not occur. Sigma z is not given here. We have to find a range of values for sigma z. Between two values, we have to find sigma z, two values of sigma z, so that yield does not occur. So we will apply maximum distortion energy criteria so that yield does not occur. Sigma x is given here. It is 100 megapascal positive. Sigma y is given 20 megapascal positive. This is small y, remember. Tau xy is given 75 megapascal. It is positive again. Okay, sigma z is not known, it is unknown. Okay, we have discussed formulas for strain energy density for a state of stress, three-dimensional state of stress. I will use the same expressions here. 1136. First, I want to find principal stresses from the given stresses. These sigma x, sigma y, and sigma tau xy are given. You can employ the expression, the formula for principal stresses, or you can use Mohr circle, whichever is required in your problem. Here there is nothing mentioned, so I am using formula. You may be asked to use Mohr circle in your exams. Okay, put all the values. You can find sigma A equal to 145 megapascal and sigma B equal to minus 25 megapascal. Sigma C, the third stress, which is in z direction, is unknown. We can see in the z direction there is no shear stress in the z plane, so sigma z itself is sigma c, which is unknown. For three-dimensional state of stress, we have discussed earlier in our theory the maximum distortion energy criteria. Maximum distortion energy criteria is sigma A minus sigma B square plus sigma B minus sigma C square plus sigma C minus sigma A square is equal to 2 sigma capital Y yield strength square. Put all the values here. 145 minus 25, so minus and minus become plus. Sigma B itself is negative. Okay, plus minus 25 minus sigma C, which is unknown, plus sigma C minus 145 square is equal to 2 times sigma Y. It is given in the problem 160 megapascal. You can find sigma C from here. Sigma C, it is 2 sigma C square minus 240 sigma C minus 650 equal to 0. It is a quadratic expression. Sigma C is actually sigma Z. We have already established it earlier. So let me replace sigma C with sigma Z. 2 sigma Z square minus 240 sigma Z minus 650 is equal to 0. It is a quadratic equation. You can find the roots of this expression. Sigma Z becomes minus 2.65 megapascal or 122.65. These two values of sigma Z are range values. Sigma Z must exist between this range so that yielding does not occur, because we have applied yielding criteria here. So this is range of sigma Z which was asked in the statement of the problem. What we have done is we have used maximum distortion energy criteria, which is sigma A minus sigma B square plus sigma B minus sigma C square plus sigma C minus sigma A square is equal to 2 sigma Y square. This Y is capital Y, yield stress. Sigma A, sigma B and sigma C are principal stresses. Sigma AB can be found from XY plane. Sigma X, sigma Y and tau XY are given. We have used expression for principal stresses. Sigma C is actually in the Z direction and there is no shear stress in the Z direction. So sigma C is sigma Z itself, normal stress. When there is no shear stress, normal stress is principal stress. So by putting all the principal stresses sigma A, sigma B and sigma C, which is unknown, in the maximum distortion energy criteria, we have found sigma C or sigma Z. The two values of sigma Z are the range of sigma Z. This was all. I wanted to explain some of the numerical problems. I have solved enough number of problems on strain energy under normal loading. This problem 11.9, 11.11, 11.12. These three problems, complicated problems on strain energy under axial loading. Then one problem on strain energy under shear loading. Then one of the problem on three-dimensional state of stress. We have already solved an example problem on beam, so you may understand expression for beam as well. So it is a very simple chapter. You just need to learn to use the expressions for strain energy under axial loading, under shear loading and under normal loading. Once again, I will write it here. These 3 or 4 expressions are very simple to be used. I will write it at the end here. For axial loading, capital U is P square L divided by 2A E. For bending, it was M square. I will confirm it again. Is integral of M square divided by 2EI and for shear loading it is T square L divided by 2 Gj. Just these expressions and you can find strain energy. Strain energy density is capital strain energy capital U divided by volume. And for normal loading it is very simple, sigma x square divided by 2E. Sigma x is stress in the direction of the load. Direction can be x, y or z. So I hope solution to these problems will be helpful for the students in order to solve all of the other problems by the students themselves.